We're looking at Chapter 4 this week, Making Sense of the Universe, Understanding Motion, Energy, and Gravity. These principles are all pretty much things that you may have learned in a physics class or maybe a physical science class. They're sort of the basic laws of physics, and of course we're applying them to the field of astronomy. So it's interesting that we come upon this a bit early in our study. The first section has to deal with describing motion, and then how is mass different from weight. Next we'll go on to Newton's laws of motion, conservation laws of astronomy, and finally the force of gravity. So let's talk about motion and mass and weight for just a little bit. Motion is described in three different ways. First, speed, and that's the rate at which something moves. Velocity, which is speed and direction, or having a constant speed moving in maybe a circular direction or one constant direction at one speed. And then there's acceleration, which is any change in velocity. Acceleration can be positive or negative. Some people call slowing down negative acceleration or deceleration. The acceleration of gravity is pretty constant, at least on this planet, but obviously is different depending on the object a person might be on. But all falling objects accelerate at the same rate, not counting friction or air resistance here on Earth. On Earth, the gravitational constant, as it's called, is about 10 meters per second. So every second that something falls, it increases by a speed of 10 meters per second. So in the example in the diagram here, after 1 second, the ball would be moving at 10 meters per second. After 2 seconds, it'd be moving at 20 meters per second. If it had another 10 meters to go, then it would hit the ground at 30 meters per second. So that's acceleration due to gravity. All objects will accelerate as they're falling. Again, depending on the object you throw it from Earth, from Mars, from Venus, from an asteroid, that constant, that gravitational constant, will be different. But on Earth, it's about 10 meters per second squared. Galileo was the first to show that the gravitational constant was the same for all falling objects, regardless of their mass. So you take a bowling ball and a feather or something very different in terms of weight, and in the right conditions, you can see that they both fall at the same rate. Of course, the feather is going to be influenced by air resistance, so you need somewhere that air doesn't exist in which you can try this experiment, and that's where it was actually done in the Apollo 15 mission. I'll try to show you that video in class. But obviously there's no air on the moon, so air resistance is not a factor. We should be able to see any two objects falling at the same rate. So momentum, it's taking two factors, mass and velocity, the mass of an object and the velocity that it's moving, that equals momentum. But if you change either one of them, you change the momentum of the object. Now the reason we're looking at this is because a lot of objects in the universe are moving in a circular or semicircular elliptical type orbit. So that's a special form of momentum. It's called angular momentum. So if something is spinning or orbiting, it has angular momentum. We're not going to do the math. We're not going to figure out what the actual value of momentum is for any object. We don't need to. We just need to know the relationship between mass and velocity, that you multiply those two and you get the momentum of an object. So if either one of those changes, the velocity of the object or the mass of the object, you change its momentum. So how is mass different from weight? Well, mass is the amount of matter an object has. No matter what its density is, it will have a certain amount of mass. And that mass is usually measured in grams or kilograms. Those are standard units of mass. Weight is different. Weight is the force that acts on an object. In other words, depending on the situation, you may have a different weight. So the example of the person in the elevator here is kind of interesting. You would have a certain weight if the elevator is standing still. You would have something different again if the elevator's rising. Different weight again if the elevator's dropping, falling. And on the far right, if the elevator's in free fall. In other words, you're falling as fast as the elevator is. That would mean that if you were on that scale, your weight would be 0. You would be weightless. So it's interesting to think about the possibilities. How could you be weightless in an area where you know you have X amount of mass and yet you would weigh nothing? Well, here's the situation we've seen with astronauts. An astronaut or in a spacecraft or even out in space, maybe doing a repair on the International Space Station, is considered weightless. There's gravity everywhere, but if you fall fast enough around the Earth, you are considered weightless. So it's a constant state of free fall. Now around the Earth, that speed would need to be about 17,500 miles an hour. So you'd have to achieve weightlessness by having a very powerful rocket shoot up and out and around to achieve that speed. So astronauts can be weightless, but they still have mass. So, how do you describe motion? Well, speed is distance divided by time. I think everybody knows that. A speed and a direction is called velocity. Any change in velocity is called acceleration. And momentum is a product of mass and velocity. And of course, angular momentum is what we see with most objects out in space, either spinning, rotating, or orbiting or revolving around another object. Angular momentum is the kind of like the subset of momentum. So how is mass different from weight? Well, mass is the quantity of matter something has. Weight is the force acting on it. We might have so much mass, and on Earth we might use a bathroom scale to measure our weight. But if we take ourselves and that same bathroom scale to another planet or the moon, the force acting on us is different. The mass is the same, but the force acting on us is different. In the case of the moon, it would be about 1/6 that of Earth. So we would weigh 1/6 of our Earth weight. So a 120-pound person on Earth would weigh about 20 pounds on the moon. And finally, objects are weightless in free fall. They have mass, but they don't have weight because they're falling as they need to be in orbit around the object. So let's look at section 4.2, Newton's laws of motion. Newton came up with these laws that are very basic, very fundamental to understanding other pieces of physics that we'll look at and apply later. But again, it's not necessary to understand all the math behind it, just the basic laws. So our goal here is, how did Newton change our view of the universe, and what are Newton's 3 laws of motion? Well, here's Isaac Newton. How did Newton change our view of the universe? Well, he realized the same physical laws that operate on Earth also operate everywhere else. In other words, throughout the universe. And so he applied these laws to all these other objects as best he could, up to the point that he could observe them. So he really discovered the laws of motion and gravity, and he saw application of it everywhere he looked. Here's Newton's first law. An object moves at a constant velocity unless something acts to change its speed or direction. This is a photograph of one of the Apollo command and service modules that eventually made it to the moon and back, orbited the moon and came back. The blue thing on the far left of the spacecraft is the rocket engine. The rocket engine didn't have to be fired for very long to escape the Earth's gravitational pull. But once it had escaped our gravitational pull, the engine was shut down and the spacecraft traveled at 25,000 miles an hour toward the moon. It did not have to use the rocket engines to continue moving. There's no air resistance, there's no drag on the object, it just moves at a constant speed. So that was for Newton's first law of motion. Here's Newton's second law of motion. A force is the product of mass times acceleration. And again, not going into all of the math, we don't need to. We're looking at page 89 here at the second law at the top of the page. The mass, say, of the baseball times the acceleration, which we can measure in maybe meters per second squared or something like that, is the force that the baseball has maybe when it reaches the home plate. It's just a numerical value that we get when we multiply those two factors. Here's Newton's third law of motion. For every force there is an equal and opposite reaction force. And this is a photograph of one of the space shuttles that went into Earth orbit and returned. Most of them did return safely. The rocket engines provided the force downward, and the reaction force was that the rocket could go upward. It did not have to push against air, it did not have to push against the ground, it just needed to push off itself in order to reach a certain speed and eventually reach Earth orbit. So it's kind of interesting that rockets like this and all the different sizes that rockets have would be able to blast off, not because the surface of the Earth was where the rocket thrust was hitting, it was because the force of the rocket engines produced a force opposite, which allowed the rocket to go upward. So this is an interesting concept, the conservation of momentum and eventually conservation of angular momentum. Any kind of momentum an object might have is not going to change unless something acts on it. It's kind of strange to think about this because we're used to maybe a car stopping after it's coasted for a little while if the engine's turned off, or something slowing down and then stopping because of air resistance. Well, in nature, with the air resistance negated or taken out of the equation, the momentum of an object keeps it moving in a straight line. If there's something else acting on it, such as a planet or a moon or something like that, that might change its direction, but it's not going to change its overall momentum. So this is a good diagram showing what's really happening here. I think this is at the top of page 91. Yeah, angular momentum. The object is moving around the sun. So as the object is moving around, it's going to be different distances from the sun. And like we learned with Kepler's laws, an object such as a planet moving around the sun is going to move faster when it's closer to the sun than it is when it's farther from the sun. The total angular momentum is conserved. In other words, it pretty much remains the same, but the speed of the planet, the speed of Earth in this case, will be changing as it moves around the sun. Now this ellipse is highly exaggerated. We're in an almost circular orbit, but just so you get the idea, the distance is smaller, so velocity is greater on the right, and over on the left the distance is greater, so the velocity is smaller. So there's this distance velocity relationship that keeps angular momentum the same all the way around. So angular momentum is mass times velocity times the radius, and of course that can be calculated for objects moving around the sun or an object moving around the Earth. We get a value that, we really don't care about the units, we just need to know that that should remain the same as long as it's orbiting the object. So the angular momentum of an object cannot change unless an external force is acting on it, and Earth experiences no external force as it orbits the sun. So its rotation and orbit will continue indefinitely. Now, that's a question that some astronomers pose to people. Will the Earth stop rotating? Will the Earth stop orbiting? Well, there's different things that might cause it to do one or the other or both. But ideally, it will continue orbiting, it will continue rotating. This is a good example of angular momentum conservation. There's basically three factors that give the capital letter F, or angular momentum, over there on the left. The mass of the object, the velocity of the object, and the radius. Well, look at this skater. The mass of the skater is not changing. But if the radius decreases, something has to change in order to keep the same momentum. Well, that's the velocity, v. So as the skater pulls her arms in, the speed of rotation is going to increase. That's angular momentum conservation. So where do objects get their energy? Well, energy makes matter move. Energy cannot be created or destroyed, but it can transfer from one object to another, and it can change in form. So in other words, energy can be converted to matter, or matter can be converted back to energy, but energy in itself cannot be created or destroyed. You can't zero it out. And there's three basic types of energy, as the book shows you. There's kinetic energy, radiative energy, and stored or potential energy. We're looking at page 92 right now. Kinetic energy is the energy of motion. Radiative energy is light. And then stored or potential energy is exactly that. It could be chemical energy, it could be energy of motion that's stored, it could be elastic energy in a spring. There's a lot of different kinds of potential energy, but the idea is that it's stored. But all these three basic types of energy cannot be destroyed. They can be converted. You could turn that kinetic energy into energy of motion, obviously, and like they show here, riding a bicycle. Radiative energy with plants through photosynthesis can make fruits and vegetables. Potential energy is obviously used as you pump your car with gas. That's converted to some sort of thermal energy and mechanical energy. But none of them can be destroyed. Well, here's kinetic energy, and something we've been aware of here through the summer. We've had some pretty high temperatures, haven't we? The kinetic energy of the particles of air that we've been experiencing have been very high. The higher temperatures mean the molecules move faster. Lower temperatures mean the molecules move more slowly. So the higher the temperature is, the higher the average kinetic energy of a substance. It could be air, it could be water, it could be any substance. We can measure the temperature of that substance, and that gives us an idea of just how active the particles are. That's kinetic energy. These are temperature scales that are used, like you see on page 93, to measure how much kinetic energy something has. Now, the Fahrenheit scale on the right is pretty common. We think of water freezing at 32 degrees, water boiling at 212. We're not going to worry about the absolute 0 point, but it's a scale that most people are used to. It's watching a weather report or checking the thermometer on your car dash, something like that. The Celsius temperature is kind of more of a scientific scale. 0 is the temperature in the Celsius scale where water freezes, whereas water boils at 100 degrees Celsius. So it's kind of like a metric scale for temperature. 0 and 100 are easy numbers to remember. It's the one on the left, the Kelvin scale, that has some very strange numbers, and the only real significant one is at the bottom. It's called 0 Kelvin. They don't even use the word degrees. It's just 0 kelvins. That's the temperature that we call absolute zero. It's the temperature at which all kinetic energy stops. In other words, the matter that had that kinetic energy, the energy is lost, and all kinetic energy, all molecular movement stops. That's 0 Kelvin, or absolute zero. We'll be looking at different temperatures in Kelvin in later chapters to describe the heat of the sun, background radiation of the universe. There's lots of ways that the Kelvin scale is used, but for now just look at it in comparison to the other two scales and realize that, well, the Kelvin scale has no negative numbers. 0 is as far as that scale can go, and it would be as far as any temperature could go in the universe. So here's gravitational potential energy. On Earth, it depends on an object's mass, the strength of the gravity, and the distance an object could potentially fall. So the example of this ball in midair is a good one, in page 94. When it's at the top of the arc, that's when it has the greatest potential energy. It has the farthest to move downward. The force of gravity is going to pull it down eventually, but that's when it has its highest gravitational potential energy. And of course, just before it's ready to hit is where it has the least gravitational potential energy. So we'll be talking about potential and kinetic energy later on in later chapters, but this is a good example of how to realize the difference. So in space, an object or a gas cloud, for example, has more gravitational energy when it's spread out than when it contracts. If it's a cloud, it has all this energy that could potentially use to contract. When it does, that gravitational potential energy turns to thermal energy. We see that in many instances out in space where a cloud has contracted and that energy is enough to possibly begin the nuclear fusion that a star uses to burn its fuel, or even the formation of a whole galaxy. So it's a very common application of potential energy turning into thermal energy that causes the formation of many things in the heavens. This is probably the easiest equation to recognize based on Albert Einstein's work. E equals mc squared. E is obviously energy. C is the speed of light, and the little 2 there means it's squared. M is mass. Well, if E equals mc2, that must mean that energy can be converted to matter, or matter could be converted to energy, and that is true. Only a small amount of mass can release, a very small amount of mass can release a great deal of energy. And of course the opposite could be true too. Concentrated energy can spontaneously turn into particles, or matter, mass, in what are called particle accelerators. What you see on the photograph there is a hydrogen bomb. It's the product of fusing hydrogen atoms, and in the process there's a huge release of energy. It's called nuclear fusion. This is an uncontrolled version of nuclear fusion, and it's the same form of energy mass conversion that is happening in the interior or the core of the sun. Nuclear fusion is the way that's all happening. When the war ended as a result of the dropping of 2 atomic bombs in Japan, that was due to a different type of bombs called nuclear fission, where uranium atoms were split or splitting in an uncontrolled manner. This is nuclear fusion, where hydrogen and helium atoms are combining to form heavier elements, but releasing a very, very large amount of energy. So we'll obviously see applications of this when we study the interiors of stars. So, what's the conservation of energy? Well, energy can be neither created nor destroyed. It can change form or be exchanged between objects. The total energy content of the universe was determined in the Big Bang and remains the same today. So if somebody had a good enough calculator, they could theoretically figure out how much energy was released by the Big Bang. And of course, how much matter was the product of that and what's happening to it. But the system in total is pretty much confined. We're not going to be able to create more energy or create more matter just out of the blue. It's going to happen. It's going to have to happen as a result of conversion from one to the other. So what keeps a planet rotating and orbiting the sun? Well, that's conservation of angular momentum. And where do objects get their energy? Well, there's the conservation of energy, which means energy cannot be created or destroyed, but only transformed from one type to another. And there are three types of energy: kinetic, potential, and radiative. So at any point in time, you should be able to recognize what form of energy something has: kinetic, potential, or radiative. The last section has to do with the force of gravity, which is obviously keeping a lot of things in line, not only around our planet with all the satellites and spacecraft that we have, but also the planets and all the other objects orbiting the sun, even the force of gravity that's keeping everything in line to create what we call collections of stars or galaxies. So what determines the strength of gravity? How do gravity and energy together allow us to understand orbits? And how does gravity cause tides? Tides are something we obviously don't have to deal a whole lot with here in Illinois, but on any of the coastlines or shorelines next to a larger body of water, tides are a major factor. They have to be accounted for if you're doing any kind of boating or fishing along those shorelines. You need to know when the high and low tides are occurring. So here's the universal law of gravitation. First, every mass attracts every other mass. So theoretically, two people standing next to each other are gravitationally attracted to each other because they both have mass. 2, attraction is directly proportional to the product of their masses. So obviously, the bigger the mass, the more gravity the object has. And number 3, attraction is inversely proportional to the square of the distance between their centers. Again, we're not going to worry about the math. Just understand that the farther away an object is from another object, the less gravitational pull will occur, the less gravitational force they will have. So in the example there that you see with the two spheres and the arrows, the blue arrows, the force of gravity on or within each other between the green and the brown sphere, it appears they're pretty much the same. M1 and M2 are the masses of the objects. D is the distance between the two. So if the mass of one or the mass of the other or the distance between them change, that changes the force of gravity. So anybody could take these a formula such as this and figure out the gravitational force between the objects. The capital G is the gravitational constant. So we could plug that number in, plug in the masses of the two objects, come up with the distance between the centers of the two objects, and we would have the gravitational force that they're being attracted by. But the main thing, again, is to remember that it's mass and distance that determine the gravitational force between two objects. Mass of the two objects and the distance between them. So how does Newton's law of gravity extend Kepler's laws? Well, Kepler's first two laws apply to all orbiting objects, not just planets. And ellipses are not the only orbital paths. Orbital paths can be bound, which means it's an ellipse, it's a true orbit. So the grayish ellipse there is something where a planet is going to move around the sun in an ellipse. And then there are what are called unbound, which would mean the object comes in, swings around the sun, and goes right back out again. And the two types are an unbound parabolic orbit, which is a little rounder, and an unbound hyperbolic orbit, which is a fairly thin orbit. Any one of those are called orbits, but Newton's law of gravity takes care of explaining how those orbits will occur. And with the help of the math behind it, has helped us many times in reaching other objects in the solar system, including Pluto, that we did a close flyby of this past summer and got some amazing pictures of that object. So how do gravity and energy together allow us to understand orbits? Well, the total orbital energy stays constant if there's no external force. In other words, there's going to be no change in the orbital energy of one object orbiting the other. Orbits cannot change spontaneously either. In other words, an object is not just going to fly off into space. It's going to move around the sun or whatever in a very predictable path. We just need to know the math. So what about changing an orbit? What can make an object gain or lose orbital energy? Well, there might be some type of drag on the object. Looking at page 97 here, there could be another object in the path of one object that would allow it to swing around it and actually take advantage of the gravitational attraction it has, and could actually aid an object to move farther out into the solar system with that energy being gained. So a gravitational encounter or a flyby, such as we've done with many spacecraft, enables us to reach other parts of the solar system without having to use a lot of fuel. So it is possible to take advantage of the orbit of, or take advantage of the gravitational attraction of one object moving around another. And then there's escape velocity. Escape velocity is when an object can gain enough orbital energy that it may escape from, in this case, the Earth. In other words, change from a bound to an unbound orbit. And escape velocity for Earth, it says it's 11 kilometers per second or 40,000 kilometers per hour. I think a better number to remember is 25,000 miles per hour. That would be the escape velocity for Earth. An object more massive would have a higher escape velocity. Less massive, a lower escape velocity. But for Earth, it's about 25,000 miles an hour. So for a mission that had to get to the moon, let's say, manned or unmanned, it really doesn't matter. The rocket that would propel the people or the object, the machinery, whatever it was, would have to move at least that fast to escape Earth's gravitational pull. Once it had escaped the gravitational pull, then it could coast, basically. It could turn off its engines and continue moving in the same direction. So last but not least, how does gravity cause tides? We're looking at something like a diagram on page 99. This is, again, something that in Illinois we don't have to worry a whole lot about, but it's happening on shorelines around the world that they have large bodies of water, such as a sea or an ocean. The blue elliptical area that you see there are the Earth's oceans. So it's obviously highly exaggerated and much thicker than we would normally see. But what's interesting is the force of gravity being exerted by the moon and the sun actually have an influence on the Earth's oceans. The moon's gravity pulls harder on the near side of the Earth than on the far side. So you can see the kind of the lengths of the arrows there. The length of the arrow on the right side is longer, meaning the strength of gravity is stronger on that side. So the Earth's oceans are actually going to be pulled or tugged toward the moon on the right side. On the left side, they're somewhat weaker. And of course, the top, the bottom, they're sort of stretched out. It also does stretch Earth. I mean, the Earth itself, the solid Earth, is theoretically distorted by the moon's gravitational pull, but you know, who's going to measure it? It's the Earth's oceans that we see the difference. And here's where we see a difference as the Earth rotates and as the moon revolves or orbits the Earth. This is probably the best example. In the top part of that diagram, looking at page 100 here, we have something called spring tides. Spring tides occur at new and full moon phases. If the sun is over on the left side of this page and we see the moon on the left, then we have a new moon phase. Obviously what we see from Earth is a new moon. 2 weeks later we see a full moon phase. Well, those two phases are responsible for extremely high tides because the moon is either in line with or on the same side as the sun. So the combination of the sun's gravitational pull plus the moon's gravitational pull will stretch out the oceans and give us high tides and low tides. So if you can for just a second, imagine the Earth rotating inside that bulge. That means that every 6 hours or so, the Earth's oceans will experience high tide, low tide, high tide, low tide. So for a 24-hour period, there's going to be 2 high tides and 2 low tides. Now, the same is going to be true in the bottom picture. Those are called neap tides. Neap tides occur at first and third quarter phases. We know our phases now, right? So first and third quarter, or first and waning quarter, whatever you want to call it, last quarter, those are 2 phases where the sun and the moon are at right angles to each other. So if the sun's pulling in one way and the quarter moon is pulling at a 90-degree angle to it, it kind of balances out. So the tides aren't going to be quite as strong as it would be in a spring tide situation. Those are called neap tides. So we have 2 types of tides depending on the time of the month, or more specifically the phase of the moon. New moon and full moon phases will experience spring tides. Quarter phases will have neap tides. Now the difference between those two might be, or I should say the tidal range, let's say in a spring tide phase, is all dependent on the shoreline and some other features that might be along the shore, but there could be a difference of as much as 50 feet between high tide and low tide. So if you had your beach towel out on that shoreline at low tide, at high tide, that beach would be 50 feet underwater. You just have to realize what the tidal range is in order to understand that it could be fairly drastic change within a 6-hour period. And there's something else that's happening here that's kind of interesting. The fact that as we're rotating, there's some tidal friction. The water of the Earth is actually generating friction against the surface of the Earth. And over time that apparently is actually slowing down the Earth's rotation. And as a result, the moon is actually increasing its distance very, very gradually from Earth. Nothing we have to worry about, but the theoretical difference is enough there that people can actually measure it. And here's an interesting situation just to kind of wrap things up. What if the Earth didn't rotate? What would be happening here? Well, if the Earth didn't rotate, we'd have tidal bulges oriented along the Earth-Moon line. So they would be in direct alignment with the moon, and we'd know exactly when high tide and low tide would be occurring. But because the Earth rotates, it's kind of causing a drag in the tides. So there's a little bit of a difference between when the moon is full and when we actually have a high tide. So the best way to actually predict when high tide and low tide occurs is to look it up. There are almanacs that publish tide times. You can buy or find an app on a phone that will give you those times. It just depends on the location, the actual geographic location. You know, latitude is a factor, but certainly the geographic location can make a difference too. So anybody concerned with, let's say, boating or fishing or something like that, would again want to know what those times are, because the Earth is rotating and it's causing this kind of a drag effect on the Earth's oceans. So what determines the strength of gravity? Well, it's directly proportional to the masses, inversely proportional to the distance. So if you increase the masses of one or both of the objects, you're going to increase the gravitational pull. And if you increase the distance between two objects that are gravitationally attracted, the gravity will be less. And how does Newton's law of gravity extend Kepler's laws? Well, they apply to other objects, not just planets. You can have different orbit shapes, and the laws can be used to measure the mass of orbiting systems. As we'll see later, we not only have measurements or calculations of objects now moving around the sun that we're recently discovering, but now we're looking at other solar systems and understanding more about planets revolving or orbiting other stars. How do gravity and energy together allow us to understand orbits? Well, a change in total energy is needed to change an orbit, and if you add enough energy, you reach escape velocity and the object leaves orbit. Finally, how does gravity cause tides? Well, the moon's gravity stretches the Earth and its oceans, but the oceans are fluid, so they react to the gravitational tug of the moon and the sun, and by that we see different heights of the ocean level depending on where we are on the Earth and what phase the moon is in. So that's pretty much it for Chapter 4. When we get together next week, Tuesday, we'll be looking at some of these phenomena. We'll be doing some activities related to them, going to the computers, maybe doing some work with tides as well. So we'll see you next week.